Okay, so now we're ready to start thinking about why it's important to deal with common denominators and when we are working with fractions. Okay, and so to sort of motivate this and to use one of the models, the measuring model, to make sense of why this is important, let me ask you a question. What's bigger, 5 or 3? Right? And of course you're going to say, well, 5 is bigger. Would it change your mind if I said, what's bigger, 5 feet or 3 miles? Right? Now, clearly, the 3 is bigger, right? 3 miles is so much bigger than 5 feet, right? So much longer, so much larger. And this kind of thinking is the same reason why if I have 5 over, let's say, 10 and 3 over 2, right? Now, on the one hand, we may be tempted to say, think about it, well, I know that 5 is bigger than 3, so then 5 over 10 should be bigger than 3 over 2, right? But on the other hand, this 5 is talking about this unit in the same way that here we said we were talking about feet as a unit. This 5 is talking about tenths as a unit, right? We can rewrite 5 tenths as 5 of these things that are tenths, okay? And this 3 halves, well, it is 3 something, right? But we can rewrite it as 3, I bet you can see where this is going, 3 of these things that are halves. So it's not just important about, let's use a different color, it's not just important about how many of these things we have. It's also important about how big each one of those things is, in the same way that feet, right? Feet is very different from miles, okay? So this is why if we wanted to compare feet to miles, we would have to say, well, how many feet are there in a mile? Or we'd have to say, how many miles are there in a foot? And that's really the principle behind working with fractions, finding common denominators. So let's take a look at what this looks like. So for example, let's say we want to compare two fractions. We want to compare 2/7 and 1/3 and say which one is bigger. Now again, I can't just say 2 is bigger than 1. I can't say 7 is bigger than 3, right? I have to sort of put them in the same unit. I have to get this denominator, right here the same, because remember in the measuring model, this is like the length of our ruler, right? And so we want to have the same length ruler, and then we can start comparing, right, the numerators on top. We can say, well, measured with the same ruler, which one is bigger? And then we can say something like 2 is bigger than 1. Okay, so how do I get 7? 7 is our denominator here, and 3 is our denominator here. How do I get them the same? Well, the easiest way is to just multiply them together. That is going to be our common denominator, right? So we can rewrite it as follows. So let me just copy down what we have. We have 2 over 7. And I want to turn that into, have a common denominator when 7 times 3 is 21. And so the question is, what would I have to do to move from 7 to get to 21? Well, it's exactly what we said, right? We would multiply it by 3. But I can't just multiply the bottom, right? The denominator by 3. I'd have to multiply the numerator by 3 as well. Because then, right, essentially you're multiplying by 1. And multiplying by 1 doesn't change anything, right? So, okay, 7 times 3 is 21. 2 times 3 is 6. So in other words, 2/7 is the same as 6/21. And let's do the same thing with 1/3. Now in this case, we're going to multiply the top and the bottom by 7, right? Because we want to end up with something over 21, right? That's the whole purpose, because then we can have the same ruler, right? The 21s would be the same. The length of the ruler would be the same. And so here we have 1 times 7 is 7. Now we can compare which is bigger. Now, since they have the same common denominator, it is okay. We can just compare the numerators and say, what's bigger, 6 or 7? Well, clearly 7 is bigger, so it turns out that 1/3 is larger than 2/7. You could even put it in your calculator. This thing is going to be something close to 0.28. This thing, I think, is going to be something close to 0.33. And, right, this one is in fact bigger. Okay, that's great. So let's do one more quick example. This also shows up when we are adding or subtracting, right? So if I wanted to find the sum, 3/4 plus 5/2. Oh, well, you say that's easy. All we have to do is go 3 plus 5 is 8. 4 plus 2 is 6, right? And we're done? No way, no house. No, this is incorrect, right? The only way that we can add 3 of something is if we're adding the same thing, right? I don't have fourths here, I have halves. I can't add, it's like adding apples and oranges here, right? So this 4 and this 2 is problematic. We need to get them to be the same number. Now in this case, it's pretty straightforward because I can have 3/4 and I'm adding, well, if I want to change, here's my 5/2. If I want to change that into fourths, right? If I want to change it into fourths, which I do, because then I would have the same denominator, right? This is my goal, right? So, well, to change a 2 to a 4, it's pretty easy. I just multiply by 2. Multiply on the bottom and the top, right? There we go. We're basically multiplying by 1 again. So 2 times 2 is 4. 5 times 2 is 10. And now, instead of writing 5/2, I can write 10/4. And that's really good for me. Now I have the same denominators. I can add the numerators, right? Now this is very easy for me to add. So 3/4 plus 10/4, that is going to equal 13/4. And I'm done, right?